Okay. 2.3 extension, the Equilibrant navigation applications and incline applications. And see, I spelled Equilibrant wrong here in the beginning. There's an R right there. Okay, so what is an equilibrant vector? So we've already discussed if we have two vectors acting on a plane, we can add those two vectors, we can find the resultant of those two vectors by using the parallelogram method, or head to tail. And so this would be the resultant of our two vectors. So if we had this vector v and this is vector u, then this is the resultant here of the two vectors. So what does the equilibrant do? Well, the equilibrant balances the resultant. It's the force that it counterbalances it. So it acts in the opposite direction. Let's do this in purple. As the resultant, but it has the same magnitude. So this is the equilibrant. Alright, so what is the equilibrant vector? It is a vector that counterbalances the resultant. With equal magnitude but opposite direction. Period. Okay, so that's it. So if we were to add the equilibrant and the resultant together, we would get 0 magnitude and direction. Alright, so here we have an example. Let's take a look at this. Find the magnitude and direction of the equilibrant for two forces, one 35 tons, the other 60 tons, both acting on point A with an angle between the forces of 55 degrees. Find the angle between the equilibrant and the 35-ton force. Okay, so we have a point A, and there are two forces acting on that point. So one is 35 tons. So this is my 35-ton force. And then I have another force that is 60 tons. So I'll draw this one a little bit bigger, longer. So this one is 60 tons. And the angle in between them here is 55 degrees. So we want to find, we have to find the resultant and then the equilibrant will be the opposite direction but the same magnitude of that resultant. So how do we do that? So first we need to find the resultant. So we can take this vector and put it over here, and this vector and put it over here. So I've got my parallelogram, and I'll use a different color here. My resultant's going to be this. Let's say a different color. So here's the resultant. But I have to actually find the resultant here. So what do we know about parallelograms? So the opposite sides are congruent, and the opposite sides are also parallel. So if this angle is 55, I know this angle over here, because same side interior angles are supplementary. So this one would be, this angle is going to be a 180 minus 55, which would be 125 degrees, right? So 125 degrees there. So this side also over here is going to be 60 tons. So what do I have here? I have side, angle, side. So let's see, that's A. Let's call this, why don't we call this B over here, and we can call this side C. So my resultant is little c. 60 tons would be little a, and 35 tons would be little b. Alright, so I'm going to use law of cosine. So law of cosine states we've got c squared equals a squared plus b squared minus 2bc cosine c. Alright, so c squared equals, alright, A is 60 tons, 60 squared plus B is 35 squared minus 2. Let's see, I'm running out of room here. Let's put it over here, I guess. Cosine. Alright, so minus 60, 60, and this is 35. Trying to color code it here a little bit. And my angle is 125. Okay, so let's see here. Let's put this. I should have had my calculator ready there. Alright, my calculator's coming up. What are we doing to this? We got, so C is going to be the square root of whatever this answer is right here, and that's going to be the resultant. Alright, so let's go down to my calculator here. Alright, so what do we have? We've got 60 squared plus 35 squared minus 2 times 60 times 35 times cosine of 125. Okay. And now, so 7234, we're going to take the square root of this answer, and we get 85.05. So we get 85.05, I guess we could just say 85 tons. All right, so the resultant is 85 tons, so the equilibrant has to be the same magnitude, but in the opposite direction. So the equilibrant is going to be this direction, and it's also going to be the same magnitude. And so it says find the angle between the equilibrant and the 35-ton force here. So what would that be? Here's the 35-ton force, so it's asking for that angle right there. So how do we get that angle? Well, I know this angle and this angle are 180. This is a linear pair right here. So I need to find this angle. How can I find this angle? This angle is angle A right here in our triangle. So I need to find angle A. So let's see. A, I need to find. I know angle C is 125 degrees, and I know little c is 85. Angle B I don't know, but I know little b is 35, and little a here is 60. So I know all the c's here, and I know little a, and I don't know big A. So this tells me to use what? Law of sine. Okay, so law of sine, and I'm looking for angle A. So how about we use sine A over little a equals sine C over little c. So sine A equals A sine C over little c, and then I'm going to take the inverse sine of that. Okay, so let's put it in here. It's going to be the inverse sine of a 60 sine 125 over 85. That's going to give me my angle. So we've got 60, so we're going to do the inverse sine of 60 sine, oops, I got to back up here, 60 times sine 125 divided by 85. So let's see, make sure I got the right amount of parentheses. Yep, that's what I want. 35.3. 35.3 degrees. That's this angle here. This is 35.3. All right, so the angle that I want right here, this angle again, is going to be 180 minus 35.3. So 180 minus 35.3, 144.7. 144.7 degrees. Okay, so the equilibrant is 85 tons at an angle of 144.7 degrees from the 35-ton force. Equilibrant is 85 tons. 85 tons at an angle of 147 degrees. And let's okay. And that's our answer. Okay. Why don't we stop there for example 1.